Hello and welcome to this Living Lab lecture. My name is Florens Rohde. I'm working at ScaDS Leipzig and I will give you an introductory talk on privacy-preserving record linkage and our work. So imagine you're a data scientist trying to develop an algorithm that recommends medical treatments based on the condition of patients. For that you need training data that might look somewhat like this table, containing information on the rough age, diagnoses, treatments and the outcomes. However, the data in this table is probably the result of a data integration process because the data is not available from one source but may be fragmented at multiple data owners, for example hospitals. At the data owners, the information is linked to personal identifying attributes such as name, date of birth, etc. And in order to combine all information that belong to the same individual, we must detect which record of one dataset corresponds to which in the other dataset. And that task is called record linkage. When working with personal data, such as in this case, the privacy must be preserved. And one basic principle is the separation of identifying and sensitive data. So the researcher does not need to know and must not know any personal identifying information from these patients. For the linkage, we only need these identifying attributes, so we might use a third party that gets these attributes and computes the links. That way, neither the data owners nor the researcher gets to know the identity of patients from the other parties. However, the third party must be trusted, as even without medical information, some sensitive information might leak, such as that a person was treated in a specific facility. PPRL addresses this problem so that no identifying data is shared between the data owners or a third party in plain text. However, before we start or before we focus on the privacy aspects, we will have a look at the conventional record linkage process because it is quite similar. Then I will introduce you to the basic methods PPRL uses, which are hashing and the most popular encoding method based on Bloom filters. After that, I will talk about the challenges in this process, especially the balance between privacy and quality. And finally, I will sum up what you might have learned. The record linkage process consists of multiple steps, with the pre-processing being the first one. The original data is cleaned and standardized. For example, by splitting the components of the name and mapping it to a common schema, or by using a common date and string formatting. Depending on the data quality, that step can already eliminate some differences between matching records, such as in this case with a German umlaut in the last name. The record linkage is based on a pairwise comparison, and those candidate record pairs have to be selected first. The naive approach is to compare each record from one source with each in the other source. However, as you can imagine, that is computationally infeasible for larger data sets. To avoid the quadratic complexity, a blocking step is used to select only those record pairs for a detailed comparison that share a common property. For example, the initials of first and last name or the year of birth. In this example, we have selected 4 out of 9 possible comparisons based on these criteria. The next step is a pairwise comparison, and we do it on the example of Philip Wolff. First, the fields or attributes of the records are compared, each with a similarity function that has a similarity score as the output. The similarity functions can be chosen per field, so that, for example, names are compared using the Levenstein similarity, but there are also similarity functions for numerical data and so on. Finally, the field similarity scores are aggregated to a record similarity score, which might be simply an average, such as in this case, but we could and should also use weights to take the different discriminatory power of the attributes into account. So, for example, an agreeing date of birth is a stronger indicator for a match than the same gender attribute. The result of the comparison step is a matrix of similarity scores for all records selected in the blocking step. Now, a binary decision must be made on these potential duplicates. For that, a threshold is chosen and everything below it is considered a non-match, such as in this example, the pair in the middle. However, records can still have multiple duplicate candidates in the other source, under the assumption that the data sources are clean, that is, they do not contain duplicates in itself. Some links can be discarded in a post-processing step where a stronger link is available. So here we have an example for that too. Finally, we have links between records considered as duplicates and can generate and send unique record IDs to the data owners, which they can use to link the data. When we switch to a basic PPRL scenario with two sources on the top and a linkage unit on the bottom, you will find these 4 steps again. However, they are separated in 2 domains. The pre-processing is done at the data owners because they rely on plaintext. After that, there is an additional encoding step. The basic idea is that the plain data is transformed into an encoded representation before being shared with a linkage unit, where the record linkage is done on the encoded data only, using blocking, comparison, and classification steps similar to those we have seen before. The data owners must agree on common parameters for the preprocessing and the encoding to ensure that the same plain data is transformed to the same encoded data to be comparable. The linkage unit, however, must not know these parameters because otherwise it could run a dictionary attack on the encoded data. We will come to that in a second. So before sharing identifying data, it must be transformed into a representation that can be compared but not be reverted back to its original form. And many of you might immediately think of hash functions. So if we hash, for example, for the names Felina and Philip, we get different hash values. And we can determine that the attributes are different without knowing the original plaintext values. Although the hash cannot be directly reverted, it is not resistant to attacks, as the hash function is publicly known, and an attacker with access to the hashes who knows that its plain data were names can grab a telephone book or any other source of names and hash all names until he finds a match, and thereby the plain text name for that hash. That's why we need keyed hash functions, where the output depends on a secret key that the data owners must agree on. Without that key, dictionary attacks are very difficult because an attacker would have to try all names with all possible secret keys. So if we encode the name Philip again, but with it we get the same hash, but a different output for a different secret key. Simple hashes, however, have no error tolerance because they are designed in a way that a small change in the input leads to a completely different hash. So for error-tolerant comparisons of encoded data, the use of Bloom filter encodings was proposed by Schnell et al. In 2009. A Bloom filter is a bit vector of fixed length that is initially filled with zeros. And the encoding works in the following way. So the plain data is split into tokens, for example, overlapping trigrams. And each token is then hashed multiple times, and the hashes are mapped to positions in the Bloom filter, which are then set to 1. If we do that for all tokens, we get the final Bloom filter. And the Bloom filters can be compared using set similarity functions, such as Jacquard or the dice coefficient. I won't go into detail here, but you can see an explanation in the Living Lab demonstrator. Now that we've gone through the record linkage process and the basic techniques that are used to preserve the privacy of the individuals to be linked, what are the challenges in this process? So the first aspect we've already touched, it's a scalability problem. So how to achieve fast linkage for large data sets. Bloom filter encodings are very popular because they not only allow for approximate comparisons, but they are also computationally cheap to compare. However, techniques to reduce the number of comparisons are still essential. We did some work in our research group on blocking techniques on Bloom filters using locality-sensitive hashing and metric space filtering approaches that make PPRL scalable to large datasets. Although the encoded data cannot directly be reverted, it can nevertheless be attacked. So methods are needed that prevent those attacks. We will come to that in a second. The linkage quality depends, of course, on the quality of the original data, because if all data sources were up to date and would not contain anything or erroneous values, we would only have to check for equality. But in the real world, we have errors such as typos, missing values, exchange attributes, people move, marry, and so on. So methods are needed that can deal with those real-world errors. Furthermore, it must be ensured that the data owners encode their data in exactly the same way, because otherwise the encoded data is not comparable. For that, they need a way to agree on the parameters to be used, and especially on the same secret key. Last but not least, for sure, is the legal aspect, because for real-world linkage projects, of course, a legal basis is required. In the remaining time, I will focus on the two aspects of privacy and quality. As I've mentioned, Bloom filters are susceptible to certain attacks. So if an attacker has access to a larger amount of Bloom filters, she can analyze the frequencies of those filters in the encoded dataset. And if she has also access to some statistics on frequent names, for example, by parsing a telephone book or just any public statistic on that, she can sort both lists by the frequency and try to align them, and thereby find a possible plaintext for a Bloom filter. That is called a frequency attack. If she succeeds, then the problem transforms into a known plaintext attack, and the attacker can then try different encodings until she finds the parameters used to recreate the Bloom filter, and then launch a dictionary attack to decipher the rest of the Bloom filters. Frequency attacks can also be extended on patterns of co-occurring bit positions and so on. And the reason why all these attacks are possible is that the encoded data shares frequency patterns with the plain data. Up to now, I have shown only field or attribute level encodings, where for each field a separate encoded representation is used. To make frequency attacks harder, a variety of alternatives was proposed. One of the widely used are cryptographic long-term keys. They are created in the following way. So first we create field-level Bloom filters, as we've seen previously. So for each attribute, a separate Bloom filter. And then we combine this Bloom filter into a joint record-level Bloom filter using a bitwise OR operation. Of course, the cryptographic long-term key still contains these frequency patterns, but it is now harder for an attacker to extract and use that information. Other approaches use different encodings for attributes, so that, for example, the token ER in Peter is not hashed to the same positions as ER in the last name Fisher. Or we might use a stable key, such as the year of birth, as an additional salt for the hashing, so that Peter, born in 1964, is encoded in a different way than Peter from 1980. Other hardening techniques take the pre-final Bloom filter and perturb the bits in it. The common goal of these encoding variants is that they want to perturb frequency patterns of the plaintext dataset without losing the ability to detect duplicates. Here we see an example that illustrates this problem. So we have two Bloom filters that are quite similar, but have some differences. As we have a binary classification problem, a decision must be made whether those records are considered a match or non-match. If we decide for a non-match, we could be wrong, because all differences in the Bloom filter are due to a different address, because a person moved. However, if we decide for a match, we could also be wrong, because the Bloom filter differences are the result of differences in multiple attributes, such as first name, last name, and date of birth, which are somewhat similar, but nevertheless, these records are clearly not the same person. In any non-trivial linkage process, there will be classification errors. Methods evolve and get better, but still there are uncertain cases. And in conventional record linkage, uncertain record pairs can be manually inspected and decided on, and that information can also be used to improve or tune the algorithm to make better automatic decisions. In the PPRL context, however, that is not possible, as a linkage unit has no access to the plain data that could be shown to a human reviewer. So the general conflict in PPRL is that the data owners want or should share as little information as possible, but as much as needed to facilitate a correct decision on match or non-match. And all records have to be encoded the same way, so we can either choose an encoding that tolerates a variety of differences but is more prone to attacks, or use an encoding that is more secure but also allows a linkage unit less flexibility in the linkage process. One approach to cope with that dilemma is to design a linkage protocol where we have more control over the encoding and matching settings and can adapt them to the problem. PPRL does not mean that everything should happen in a black box and without interaction to achieve privacy by obscurity. That's not the goal. The linkage unit is a place where the decision on potential duplicates are made, and where it becomes clear whether the provided data is enough for certain classifications. However, the linkage unit has no control over the encoding, which determines which differences can be tolerated by the algorithm. So the idea is to use multiple stages or encoding rounds where the data owners and the linkage unit interact. So first, universal encoding with a high level of privacy protection is used to determine certain matches and non-matches. For the uncertain cases, a more flexible encoding is requested from the data owners that allows the linkage unit to use more information for the classification. These flexible encodings are more safe to use at this stage because not all records have to be encoded the same way, because those that have to be compared were already identified in the previous stage as potential duplicates. And if even that encoding is not enough for the linkage unit to make certain decisions, a third stage might be used where the plaintext for differing attributes is requested and displayed in a masked form for manual human review. So for example, it is only shown which attributes are equal, which are completely different, and for similar attributes only a masked diff is shown. And the decisions in later stages can also be used to adapt and improve the previous stages in a feedback mechanism. This protocol acknowledges the fact that there is no encoding that is optimal for all datasets or all records in heterogeneous datasets with different types of errors and so on. To implement such a flexible workflow, apart of course from a workflow management system, a toolbox is required that provides different encodings and matching strategies. For that, our group is working on a toolbox called Primat, Private Matching Toolbox. It provides implementations for components of the whole PPRL workflow, especially state-of-the-art encodings, blocking, and post-processing methods. End of advertisement. To sum up, so privacy-preserving record linkage enables the data integration of sensitive information by linking records between multiple data owners without exchanging any identifying information with each other or a third party. For that, the plaintext is encoded before being shared, and there's a variety of available encodings, for example simple hashes and Bloom filters, we've seen those. We have also seen the technical challenges in this problem. There is scalability, privacy protection against attacks while maintaining a high linkage quality and interoperability. I've also mentioned our research topics. So we have done some work on the scalability of PPRL for large data sets. We're evaluating encoding methods with regard to their privacy protection and achievable linkage quality. And we are working on protocols that allow for a reliable high linkage quality on datasets with unknown properties. So, for example, which error types occur and so on. If you want to know more on these aspects, you can have a look at our publications. And of course, I'm happy to answer questions in the following discussion. Thank you very much for listening.